Hello everyone, welcome back to Physics 40C. This week we're going to be doing a little bit of a mid-quarter review, and so we'll be talking about the chapters that we've covered up to this point, and I'll be highlighting probably the most important, or at least the most often used formula for each one. Now, just a disclaimer, this is by no means a comprehensive study guide as you go into midterms. Definitely, I would recommend watching the other videos that we've done throughout this quarter to do a more thorough review, and then also reviewing lectures and notes and things like that. This is just going to become a brief overview, maybe to give you the names and the topics that we covered, and the key formula to kind of get you started in your studying. So the first chapter we did, well, so far we have done chapters 22 through 27. And so chapter 22 was electric charges and forces. And so this is where we were first introduced to the concept of a charge and the fact that they can generate forces against each other. So the main equation that I chose was F equals K Q1 Q2 over R squared. So when we're just looking at the magnitude of a force, we put the absolute value signs in front of the Q's, just to remind you that, so this is the force magnitude, but you typically report force as a vector. And so you can actually indicate that using this R hat term there. And so this is just to remind you guys that each charge has a unit of coulombs. So we have 2 coulombs there. Then we have R squared, the base unit is meters squared. So sometimes it's centimeters or nanometers or something like that. But meter squared is what we consider the base unit. And then we have Newton meters squared per coulomb squared. And that's K. So all of these units end up canceling out to make force equal to, or it has a base unit of newtons, right? So this is a brief reminder to you guys, hopefully it's a refresher, that positive or opposite charges will have an attractive force towards each other, and similar charges will have an opposing force towards each other. So that can be important in providing the direction of your force, because a vector has both magnitude and direction. So you use this formula to find your magnitude, and then you have to look at each situation to find your vector direction. So for chapter 23, draw a line there, we had the electric field. And so the formula that I chose for this one is E equaling K Q1 over R squared. So this is almost exactly the same as the force equation, but force divided by a charge. And so this has base units of newtons per coulomb. And so this is hopefully also going to be a little bit of a reminder, but positive charges or positively charged objects will emit an electric field going outward. So a point charge like this will have an outward facing charge. I tend to think of it as, I don't know, positive people tend to have a lot to give and they want to project out onto others, whereas negative people tend to be, I hate to make stereotypes, but they tend to, be very self-focused, and they tend to take a lot from what's around them. So we draw the arrows this way. And so just as the equation indicates, you don't need two charges to have an E field. So these charges have E fields kind of independently of another. They don't have to interact, but they can. It just, each charge has its own E field. So when you're summing up a bunch of E fields, or there's multiple charges in a situation, you have to calculate the E field for all of them. So this next bit, we have chapter 24, which is Gauss's law. Gauss's law for me was probably, it's not the most complex in the mathematics of it, but for me it was the most difficult to understand when I took this class. But you know, after looking through it a couple more times, I've kind of started to develop a really decent understanding of it. So here we have flux. So this is really important when we deal with Gauss's law. When you see the word Gauss's law, I want you to think flux. And when you see the word flux, I want you to think Gauss's law, because the two are so closely related. So whenever I say Gauss's law, I'm going to write the equation for flux. We don't call this like a Gauss or something like that. We instead choose to use the more mathematical term, but this idea is what Gauss's law is illustrating. So this is flux. This weird fancy integral is just a surface. So whenever we say the term Gaussian surfaces, this is the mathematical representation of that, E times dA. And so what this ends up being is E times A that is parallel. And so one of the reasons why this was really hard for me to master was because I always got confused on what they meant by parallel. So when you have an E field perhaps flowing in this direction, and you have a, let's say it's a circular area facing up this way, I would tend to think that this meant that the area was perpendicular to the flow of the E field. But in this case, we are looking at the direction of the area vector. And so the area vector is actually the thing that's perpendicular to the area itself. So this is the area vector here. And so if I look at the two arrow shapes, these two arrows are parallel to each other. So E times A parallel is how you get the maximum amount of flux. So this would be the maximum amount of flux, so just E times the full area. But if I were to draw it this way, I have my area vector projecting at a right angle to it, or perpendicular, and I had E field flowing in the same direction. This here would be no flux, because the area vector is perpendicular. And so when perhaps you have an area at some angle, you only care about the area that is projected perpendicular. So let's see. You would only care about this area. And so if you're given some angle theta of the tilt, this also can turn into E times A cosine theta. And that just kind of represents what you're looking for. Sometimes it's easier to use sine depending on which angle you're given, but you're always just looking for the area that is the area that has the vector that is parallel to the flow. After that, we had electric potential, chapter 25. And so the easiest, or the, I guess, most fundamental equation to look at potential is the change in the E field, or the change in E field as you move along space and time. So it's ds, and then with an interval of s, I, and sf. And s is just some distance. And so this is, oh, oops, I forgot. It's electric potential and field is this chapter. And so this is the relationship between electric potential and field here. So electric potential has the units of volts, which we usually just denote by V. And so this is actually equal to just another expression for it. You get kq over r, or just Newton meters per coulomb. And there's also the relationship to potential energy, but I'm not going to cover that here. I think I covered it either last week or the week before. But this is just a really basic introduction to electric potential and how to tie all of the, I guess you would call it, really microscopic or even atomic structures of physics. So this is electrical physics, and then this is kind of our bridge into the world of circuits. So we have voltage kind of being the bridge between the theoretical physics and then more practical applications. So the last chapter was chapter 27, and that was current and resistance. And so this carried even more into circuit components and seeing how different circuit components interacted with each other. So the most basic principle for chapter 27 was definitely Ohm's law, which is V equals I times R. Now, potential and voltage are kind of two words that are used interchangeably in this class. So I want to call this voltage equals current times resistance. And so resistance has units of ohms, which is this funky symbol here, but it's pronounced just like Ohm's law. And then I is a little bit confusing because it stands for current, or we call it current, and it has units of amps. So the term I has the meaning that starts with a C and a unit of amps, which is A. So that can be a little bit confusing, but if you write it enough times, hopefully it should be more straightforward. And V just has voltage. Alrighty, I think this is about as far as I'm going to be able to get to. Thank you guys so much for tuning in. Please remember to sign in, click the link in the description if you watched today's video. If you have any questions on this or want any more help reviewing, you can definitely see our office hours, which are also in the description, and I will see you guys next week. Thanks.